So in the next step we are going to calculate design capacity. So step number 3, design capacity. For the first case, so what is the first case here? Angles placed back to back on opposite sides with longer length leg joined to the gusset plate. So what does that mean? So it means that this has got to be the gusset plate. In that case, you'll have this longer leg and this is going to be the shorter leg which is connected to the gusset plate. So we'll calculate the IYY for such case. So IYY we will calculate. So this is equals to, so we have this two angle section. So IYY for this 18.5. So this has to be 2 times 18.5 into 10 raised to the power 4 plus, you got the area that is 978 multiplied by 2 and this area multiplied by so IYY of these two angle sections plus area into y bar square. So if we just calculate here y bar, so here we will get it around 12.4 mm for the angle plus 10 mm gusset plate, and this has to be square. So you will get here IYY as 96.22 into 10 raised to the power 4 mm raised to the power 4. Now we need to calculate RYY. So RYY, it is square root of IYY by A. So you have this IYY which is equals to 96.22 into 10 raised to the power 4 and is divided by 1956, which is the area, and if you calculate this you will get it around 491.9. sorry, you will get this around, so therefore RYY which is equals to 22.18 mm. Now we need to calculate the slenderness ratio. So slenderness ratio we need to calculate so that we can check what kind of buckling class is Once we get the buckling class, and directly we can calculate the design capacity provided. So therefore slenderness ratio will be equals to L effective by RYY. Now this L effective we have already calculated, that is 2464 in the step number 1 itself, and is divided by RYY, we got 22.18. So this is coming out to be around 1.1. Now we need to use the table number 10, page number 44. From here we will get what kind of buckling class is. So we have this angle section, and here we just need to check that the first one is the cross section, then there are limits are given, then buckling about the axis, and then last one buckling class. So if you have this angle section, in that case you will get the buckling class C. So from table number 10, page 44, we get the buckling class C, and from this, now for the buckling class C we have to use table number 9C, which is on the page number 42. So this is table number 9C. It depends upon Fy, and you have this KL by R, that is 111. So it is going to be around, if you just interpolate from 94.6 to 83.7, because for 110 it is 94.6 and 120 it is 83.7. So you have to interpolate in between this. So for 111.1 we'll get, after interpolating, so now from table 9C, page 42, FCD is 93.4 MPa, that is what we get. Now we need to calculate the design capacity. So therefore design capacity, which is equals to FCD, what we got here, multiplied by the area. So FCD is 93.4 multiplied by area is 1956. So this is coming out to be 182.7 kilonewton. Now you just need to check whether this is greater than your load given in the problem. If it is given, so you can say it is safe. So since this is greater than the load given in the problem, which is greater than load of 178 kilonewton. So therefore this is safe. So that was for the part A. Now we need to go for the part B. So part B is angles placed on same side of gusset plate. So now here we can provide the different angles, because so to try we can go ahead with the two angle 80 by 50 by 10 mm. This is again from the steel table we will get, and the properties are area is 1202 mm square. Then you have this IYY 22.10 into 10 to the power 4 RXX 24.9 mm. Then we have RYY, that is 13.6 mm, and CYY you have this 13.2 mm. So now based on this we can say area provided, which is equals to 2 times 1202, that is 2404 mm square, and this is greater than your 2000 mm square what we got or what we needed minimum. Now in this case, and this is the case of back to back. And that's the reason you don't have the distance between the angle section, and so therefore IYY for all this 2, so you will have this 2 multiplied by 22.1 into 10 to the power 4 plus area you got 2404 multiplied by again y bar. Here y bar is already given, that is CYY, that is 13.2 mm, so multiplied by 13.2 square. So here we will get, therefore IYY it is 86.087 into 10 to the power 4. So just we need to repeat the same steps, having only this part is different, IYY calculation as compared to the earlier one. Now here we can again calculate, therefore RYY, which is equals to square root of IYY by A. So you got here IYY it is 86.087 into 10 raised to the power 4, which is divided by area is 2404. Therefore, you will get RYY, it is 18.92 mm. Now we can calculate the slenderness ratio. So slenderness ratio, which is equals to L effective upon RYY. L effective is 2464 divided by 18.92, so you will get it around 127. So again you need to refer from, you can say, table number 9C, page number 42. You will get the FCD so for 127 it has to be in between 83.7 to 74.3. So interpolate it, and after interpolating we will get FCD as 76.9 MPa. So therefore at last design capacity equals to FCD into a FCD is 76.9 into area 2404, and this is going to be 184.8 kilonewton. This is again greater than 178 kilonewton load, so therefore safe.